Welcome to the second lecture on digital twin Earth enabling technologies. This lecture will focus on key technical topic, which is programming for digital twin of Earth. We will diving into Python and Jupyter Notebook first, which are essential tools for our programming task. Next, we'll introduce you to Google Earth Engine. This powerful platform provides access to a vast archive of satellite imagery and geospatial data. Finally, we will discuss hiding tools for diagramming and code development. These tools will help you structure your projects, design your platform, and streamline your coding processes. After this lecture, we expect you improve your knowledge into the identification of core programming skills and tasks for digital twin Earth application development. You would gain basic information also on Python programming and Google Earth Engine, as well as on the portfolio of software tools for supporting digital twin Earth prototype application development. But let's start discussing which are the main advantages in learning programming when you work with digital twin Earth. Developing digital twin Earth application involves several layers of expertise. To ensure the success of the project, effective collaboration and communication with specialists from diverse fields, including geoscience, environmental science, computer science, etc., are essential. In addition to these collaborative efforts, creating a digital twin Earth application demands strong programming skills and commitment to stay informed also about the latest technological advancements and tools. This combination of teamwork and technical knowledge is crucial for overcoming the complexities of digital twin Earth development and achieving effective outcomes. In the context of digital twin Earth application and in general of geospatial data analysis and management, programming is a mandatory skill that enables the automation of complex procedure and the seamless orchestration of various technological frameworks and components. As we move forward these fields, there is an increasing demand for individuals who possess a strong understanding of programming. This knowledge is essential for the development of effective and innovative digital twin Earth application. At the heart of this application are WebGIS and geospatial data analysis libraries. These technologies form the backbone of many digital twin Earth solutions, allowing for efficient manipulation and analysis of spatial data. WebGIS programming is a field dedicated to the creation and enhancement of web-based mapping solutions. It involves not only the development of application, but also the integration of various tools and services for geospatial data processing. Essentially, WebGIS helps us build comprehensive solutions for specific challenges, whether by developing complete application or managing data and services for geospatial analysis. On the other hand, programming for geospatial data analysis focuses on the use of programming language and tools to handle spatial data and geographic data. This involves a range of activities from the processing and manipulation to analyzing and visualizing the data. Additionally, these fields encompasses modeling techniques that simulate real-world spatial processes. Both the aspect of programming and data analysis are requested to develop digital twin Earth application. Various programming tasks can be associated with different components of the digital twin Earth system. Here are some examples. Let's first have a look at the task related to the database and data lake component. Here, we focus on fetching the spatial data from databases and data lakes, integrating APIs for real-time data streaming, and developing code for cleaning, transforming, and harmonizing those data. This task ensures that data is accurate and readily available for future use. Then, moving on the viewers, this component involves developing web-based mapping application for interactive data visualization. We work on visualizing historical, forecast, and simulated data, and implement interface to manage simulation components. These tasks are crucial for users to interact with and analyze the data effectively. In the archive, nowcast, and forecast component, our responsibility is general to include automating data updates and backups, implementing features for managing and integrating multiple data sources, and connecting nowcasting and forecasting model with simulation components. These tasks help maintain data integrity and support accurate forecasting. Next, in the what-if simulator component, we implement the core simulation logic and develop spatial analysis scripts to run scenario simulation. We also work on features for managing and saving simulated scenario. These tasks, of course, are essential for exploring different scenarios and understanding potential outcomes of our experiments. Finally, the decision support tool component focuses on developing user authentication mechanisms, implementing decision model based on simulated data and archived data, and create dashboard or alert systems. These features are designed to support decision-making processes by providing secure access to information and timely notifications. In most of digital twiners projects, programming is a fundamental component. Whenever we are customizing existing tools or developing entirely new system, selecting the right programming language or languages is a critical part of the design process. One of the most interesting aspects of working in digital twin Earth is the wide variety of programming languages that can help us. Each language comes with its own set of strengths and it's suited to different tasks. As such, there is not a single best programming language for digital twin Earth application. Instead, many projects utilize a combination of languages to achieve their objective. By carefully choosing the appropriate language, we can better tailor solutions to meet the specific needs of our projects. Two of the most popular programming languages are for sure Python and JavaScript. Both of these languages stand out not only for their widespread use, but also for their effectiveness as entry points into the world of programming for digital twin Earths. So let's start mentioning Python first. Python is the primary scripting language employed in most of GIS software. It is often praised as a glue language due to its ability to seamlessly integrate with other languages and systems. One of Python's strengths lies in an extensive collection of third-party libraries and packages. This extension enables the user to perform complex visualization, manipulation, and modeling of geospatial data, for example. Another significant advantage of Python is that it's open source. These characteristics played a crucial role in its success across diverse domains, including web development, data science, and also artificial intelligence. Moving on JavaScript, this is instead a cornerstone of modern web development. JavaScript serves as the primary scripting language for creating dynamic and interactive user interfaces on the web. Its versatility and broad functionality make it an essential tool for developers. One of the key strengths of JavaScript is its rich ecosystem. These are numerous frameworks and libraries available, including many that focus on web mapping modules, which help developers building sophisticated mapping and geolocation features. JavaScript also boasts extensive compatibility, working seamlessly across existing browsers, and this broad support ensures that web applications built in JavaScript can reach a wider audience. Additionally, JavaScript is also open source language, which means it benefits from a vibrant and collaborative community of developers. This community continuously contributes to the language evolution, providing new resources and also support to other users. In this part of the lecture, we will introduce the main feature of Python programming language and the software tools which can be exploited to develop our Python applications. So let's start to see together more in details Python feature. Python actually it's a high-level interpreted programming language that is widely recognized for its simplicity and readability. Its design emphasizes clear and straightforward code, which helps developers write and understand programs with ease. Another significant aspect of Python that is its cross-platform, so it runs seamlessly on multiple operating systems including Windows, macOS, and Linux. This cross-platform network ensures that Python code can be easily transferred and executed across different environments without any modification. Python is also preferred language for several advanced fields. It is extensively used in machine learning and geographic information system scripting, and it holds a strong presence also in web development. This broad applicability makes Python a versatile tool for various programming tasks. Lastly, Python syntax is notably clear and concise. In fact, Python code is often one-third to one-fifth the size of equivalent C++ or Java code. Its syntax resembles pseudocode, which not only makes it accessible for beginners, but also helps the development process for experienced programming. The conceptual hierarchy to follow in Python programming is the following one. At the top level, we have programs, which are made up of different modules. Each module is a collection of statements. Within this statement, there are expressions, and these expressions are responsible for creating and processing objects. It is important to note that Python, everything you work with is connected to an object. This fundamental concept helps us understand how Python organizes and handles the source code. Now let's see one by one which are the main features of Python programming languages. First of all, we have variables. A variable in Python is like a container for the data. What a variable does is simply to reserve space in your computer memory where you can store values. Every variable must have a name, and this name must follow certain rules. First, it should start with a letter or an underscore, and you cannot use special characters. And also, you need to be careful that variable names are also case sensitive. In Python, a variable can hold only one value at a time. When you are assigning a value to a variable, you do it from the left to the right. For example, if you write variable equal value or expression, you are setting the variable to that value or result. One important feature of Python variables is dynamic typing. This means that you can change the value of a variable during the program execution. In many programming languages, and in Python so, each variable has a type. This type defines how the variable is stored and how it can be used. In some languages, you don't need to specify the type of the variable when you write your code. Instead, the type is determined automatically at the runtime. This means that you don't have to declare the types of your variables beforehand. It is important to understand that the type is associated to the object, not just to the variable name. This means that a variable can change both its type and its value while the program is running. Let's look at some basic types you will for sure encounter in your Python experience. First, we have integers, then we have strings, boolean, float, and non-type. Integers are meant for storing value without digits, strings for text, boolean for true and false statements, and floats instead can be used to encode numbers with decimals, while the non-type represents variable that does not have a value. This basic type help us to work with different kinds of data in our programming. During our programming, we can play with our variables, for example, using operators. Operators in Python are special symbols of keywords that allow us to perform various operations on operands. Operands can be either variable, but also values, or even more complex expressions. There are several types of operations in Python, but let's have a look at the most common ones. First, we have arithmetic operators such as plus, minus, times, division, which are used for mathematical calculations. Then we have comparison or relational operator like equal and mine bigger and smaller than, and so on, that help us to compare values. We have also assignment operators like equal, plus equal, minus equal, and so on, which are used to assign and update variable values. Finally, we have logical operators such as and, or, and those are used for perform logical operations. It is important to know that that precedence applied to this operator during program execution. This means that some operators are evaluated before others, which affects the results of our expressions. As we said before, you can store in your variables different data types, and Python offers several fundamental data types that are essential for programming. These include integers, floating point numbers, string, list, dictionary, tuple, sets, and booleans. Let's have a closer look to each of them. Integers, as we might know, represent whole numbers, such as 1, -5, or 100. They are used for counting, indexing, and calculation where only whole numbers are needed. Then we have floating point numbers or float. This represents numbers with decimal point, like 3.14, -0.5, and so on. They are used for precise calculation and measurements. Third, we have strings or str. Strings are sequence of characters enclosed in quotes, like hello world between double quotes, or Python with just a single quote. They are used for text manipulation and display. Lists are ordered collection of items that instead can be different data types. For example, you can put in a string integer number and strings, and like 1, 2, 3, and apple between quotes, and close that into square brackets. Lists are mutable, which means that you can change their contents after they are created. Fifth, we have dictionaries. Dictionaries store data in a key value pairs. For instance, name, semicolon, Alice, age, semicolon, 30, between brackets. And these store names and age of a person, for example. Dictionaries, instead, are mutable again, so allow a quick lookup of value based on keys. Then we have tuples. Tuples are similar to lists but are immutable, meaning their contents cannot be changed after creation. For example, if you put the round brackets 1, 2, 3 and close the round bracket, you create a tuple. Tuples are often used for fixed collection of items. Then we have sets. Sets are an ordered collection of unique items, for example, 1, 2, 3 in brackets, and it's set for numbers where each number appears only once. Sets are mutable, but do not allow duplicate elements inside them. Then we have Boolean, and Boolean represent one of the two values, true or false. They are used for conditional statement and logical operation. Data types in Python can be categorized, as you may understood, into mutable and immutable also. Mutable types, like list and dictionary, allow you to change their content after creation with your programming. Immutable types, like integer, floats, and string, do not allow change to their values once they are set. But let's see now how we can implement our automatic operation. And we do that in programming generally using control flow. Control flow refers to the order in which statements are executed in a Python program. In Python, there are several constructs we can use to control the execution of our code. This includes especially two types of control flow. One is called conditional statement, and this allows us to create a certain block of code based on whether a condition is true or false. For example, we might use an if statement to run a piece of code if a condition is met, another piece of code if the condition is not. Second, we have loops. Loops instead help us iterate over sequence of elements or repeat execution of block of code as long as a condition remains true. The most common loops are for loops and the while loops. These control flow mechanisms help us in creating dynamic and flexible programs. In Python, for example, the for loop is used to iterate over a sequence. This means that the loop goes through each element in the sequence one by one. For each element, the loop executes the code inside the loop body. In simple terms, The for loop allows us to run a block of code multiple times, once for each item in a list or a string or other type of sequences. Let's take a look on how it works. So you define the sequence you want to go through, and then the for loop will automatically handle the process of moving from one item to the next and running the code for each of them. Important is to notice is the indentation. Indentation is quite crucial aspect in programming languages, but especially in Python. While many programming languages doesn't allow you to write code in multiple lines, Python is designed to be really structured as a text, to be read by human. So Python, indentation in Python, so spaces or tab, will block your code if they are not properly placed. So if you see, for example, the body of the for loop requires 4 space indentation to be read and compiled by your Python interpreter. Another example are conditional statements. In Python, the conditional statement begins by evaluating the if statement. If this statement condition is true, the program will execute the code inside the if block and skip any remaining statement. If the condition is false, Python will check then any else if condition, if there are any. If one of these else conditions is true, the corresponding block of code will run, and the else block will be skipped. If none of the if or else conditions are met, the else block will be executed, if it's present, of course. The structure allows Python to choose different actions based on various conditions. The third type of control flow that is most popular is the while loop. Like for the for loop, the while loop allows us to repeat a sequence of instructions. However, there is an important difference between them. A for loop runs a set of number of times based on sequence of values. In contrast, a while loop continues to execute as long as a given condition remains true. In simple terms, the while loop checks the condition before each iteration. If the condition is true, it runs the block of code inside it. The process repeats until the condition became false. Now that we know the basic feature of Python, let's have a look on something more complex. Let's speak about functions. Functions in Python are named blocks of reusable code that are designed to perform a specific task. To define a function, we use the def keyword, followed by the name of the function and its parameter in parentheses. To execute a function, we simply call it by writing its name followed by parentheses. If the function requires any arguments, we can pass them inside the parentheses, though some functions do not require any arguments. Additionally, functions can return a value to the caller using the return statement written in them. When the return statement is encountered, the function stops running and the value specified is sent back to where the function was called in your code. It is important to know that in Python there are existing functions that we can call and use right away without having to define them ourselves. And those are called built-in functions. Built-in functions help us to solve common problems and perform such everyday tasks in programming. For example, the print function lets us display information on the screen. Another example is the len function, which gives us the length of a list or a string. There are also type functions which tell us the type of a specific variable, for example. These built-in functions are part of Python standard library, and they are always available for us to use in our code. Often, built-in functions are not enough for our programming needs. We have in Python essential components that help us organize and reuse code efficiently, so without the need of writing all the code anytime we need a specific function to be run. And these are modules, packages, and libraries. Let's start talking about modules. A module generally it's a file that contains ready-to-use Python code. It can include function, classes, or variable, and may also have code that runs when the module is imported. Essentially, any Python file can serve as a module. Next, we have packages, and packages is a collection of modules that are organizing into a directory structure. This hierarchical organization helps manage and group related modules together, making it easier to navigate through the code. Finally, we have when a bundle of set of related module and package together, and this is called generally library. Library are comprehensive tools that provide a wide range of functionalities for various programming tasks. In summary, we have modules that are individual Python code, individual files with Python code. Then we have packages, which are directories that contain modules. And then there are libraries, there are a collection of modules and packages all together. Generally, we need to install these packages and library from third parties, so they are not always available in our Python once we installed them from scratch. What is common to many Python function, library, and modules is that we need to call them, to import them anytime we start our scripts. In Python, import statements are used to bring modules and packages into our current work session. This is essential for using additional functionalities in your code. Python comes with standard modules and packages that are available for you to import without the need to install anything extra. These built-in resources can help you accomplish many tasks right out of the box, and those are the building function that we saw 2 slides ago. Additionally, there are many non-standard modules and packages available to external libraries. These require instead you to install them separately alongside Python in order to use them in your coding. Understand how to import these resources will for sure help you leverage a wide range of tools and libraries that your programming project might require. In the image, you can see some popular import statements to import, for example, a whole package, or only a specific module, or to import a package with a alias. So we need later less code to call the modules in our scripts. Now we have all the ingredients to start creating our programs in Python. In Python, programs are primarily written in plain text files. By convention, these files use the .py extension to indicate that they contain Python code. To run this code, we use a tool called interpreter. The interpreter acts as a bridge between the Python program and the computer hardware, allowing us to execute code interactively. When you install Python, it comes with built-in interpreters. They are also known as console, shells, or IDEs, integrated development environment. These tools let you write, test, debug, and debug your Python programs. Not by chance, most popular GIS software comes with an interface for Python scripting. This feature allows users to automate tasks, perform complex analysis, and extend the software functionality. By using Python, you can write scripts to manage spatial data, create maps, and develop custom tools. This scripting capability is a powerful way to enhance your work with GIS application and streamline your workflow in software like QGIS, ArcGIS, and GraphGIS, and not only this, but also many other GIS software. Let's see now how practically install external library and Python in our computer. To install external Python libraries in our workspace, we typically use package managers like Conda or pip. You can check their documentation online at the provided link in the slide. Once you have installed these package managers alongside your Python, you can easily install external libraries. After installation, these libraries are ready to be imported into your scripts and program, allowing you to enhance your Python project with additional functionalities. Speaking about geospatial world, Python has very geospatial libraries. These tools are crucial for supporting digital twin Earth development and are spread across different external libraries. Here, some of the most popular GeoPython libraries are listed. Shapely, for example, is used for the manipulation and analysis of planar geometric objects, like vector objects. GeoPandas is high-performance tools for geospatial data analysis, again focusing on vector data. GDAL is an essential library for processing both vector and raster data. Then we have other libraries like Fiona, facilitating reading and writing spatial data, PyProJ, that is used for cartographic transformation, Raster.io, that focus on raster data analysis, PySal, which provide various spatial analysis and spatial statistical function, GeoPy, that act as client, Python client for several popular geocoding web services, and so on. But there are many more, and if you want to find a comprehensive list of the geospatial Python libraries, you can visit the GitHub page that is linked below. As you can see, when you start to customize and add libraries to your Python installation, everything can become a bit messy. For solving this issue, a very important feature of Python is the concept of virtual environments. A virtual environment is a space within your computer memories where Python is installed along with its configuration, libraries, dependencies, and interpreters. The primary Python installation, which is often referred to as Python system or base environment, allows you to create separate and isolated environments. These virtual environments are useful because they enable you to develop distinct Python projects without conflicting dependencies or that are libraries of different versions of the same libraries or interfaces between projects. By using virtual environments, you can maintain clean and organized development setups for different projects, ensuring that each project has its specific libraries with their own version installed properly in the correct place. To better understand the virtual environment concept, let's consider a scenario when you have two projects. Let's call it Project A and Project B. Both projects depend on the same package, but they require a different version of this package. For example, Project A needs version 1.0.0, while Project B needs a newer version 2.0.0 of the same package. Without virtual environments, Python cannot differentiate between this version in its package directory. Both versions will reside in the same directory with the same name. As a result, Project A and Project B would be forced to use the same version, which is often unacceptable. To solve this problem, we can indeed use virtual environments. They allow us to create isolated spaces for each project in our computer memory, ensuring that each project can use the specific package version that it needs without any conflict with other projects. Any available Python distribution supports virtual environments. One of the most complete and popular platforms for developing and managing Python projects is called Anaconda. You can find more about Anaconda at the link provided in the slide. For our utility, we can use, and there are available advanced integrated development environments for Python. These tools provide powerful features to enhance your programming experience and productivity. We have, for example, PySharp, that is a widely used integrated development environment developed by JetBrains. It offers intelligence code completion, code inspection, and on-the-fly error highlighting, and quick fixes. PyCharm is known for its strong debugging capabilities and support for web development frameworks. Then we have, for example, Spider, which is an open source integrated developing environment specifically designed for data scientists and engineers. It integrates well popular data science libraries like NumPy, SciPy, and Pandas, and provides features such as variable explorer, interactive consoles, and support also advanced plotting capabilities. Third, last but not least, we have Jupyter Notebook. Jupyter Notebook, it's a web-based IDE that allows us to create and share documents that contains live code, equation, visualization, but also narrative text. It is particularly useful for data analysis, visualization, and also machine learning. This will be the main integrated development environment that we will use during the practices of this course. However, these are just a few of the advanced Python IDEs available, which of them offer unique features suited to different type of projects and workflow. So check it out then. Jupyter Notebook IDE is peculiar because it relies on computational notebooks, which are shareable documents that combine several elements, including computer code, plain language descriptions, data, and rich visualization like 3D models, charts, and dynamic maps and figure, and also interactive controls. These make it versatile tool for data analysis, visualization, and also communication of your data workflow. Jupyter Notebook is a server-client application that allows you to edit and run this notebook via a web browser. It provides an interactive and user-friendly environment for developing and presenting your work. The Jupyter Notebook app can be executed in a local desktop machine without requiring internet access. Alternatively, it can be installed also on remote server and accessed to the internet, providing flexibility in how you use it. The Jupyter Notebook is integrated into many user-friendly applications. The two most interesting for this course are Jupyter Lab and Google Colab. Jupyter Lab is a feature-rich notebook authoring application and editing environment. It is part of the Project Jupyter ecosystem and provides an integrated development environment for working with notebooks, code, and data. You can find more at the link provided in the slide. Google Colab instead is a hosted Jupyter Notebook services that require not set up to be used. It provides free access to computed resources, including GPUs, making it an excellent option for running computationally intensive tasks. Google Colab is especially useful for collaborative work and sharing notebook easily. So why Jupyter Notebook is so interesting for digital twinner? Jupyter Notebook offers indeed a user-friendly and versatile platform that is well suited for many aspects of digital twinner development. Its interactive nature make it particularly valuable for educational purposes, allowing students and professionals to learn and experiment with digital twinner concept effectively. Additionally, Jupyter Notebook is ideal for prototyping. It allows you to quickly test and visualize ideas, iterate on models, and presents your findings in a clear and engaging way. The ability to combine code, data, and rich visualization is in one document enhance collaboration and communication among team members. Overall, Jupyter Notebook is an excellent tool for advancing digital twin project from initial concept to more developed prototypes.